All right, jumping back to one that uses the AMBBLP, I'm going to go with CO2. How do I know it uses AMBBLP? It does not have a halogen present. There's no externally bonded halogen, carbon dioxide, so we're going to use ANBBLP, which is a little bit different process, gives us the same information ultimately, but a little bit different in terms of the calculation. The more you practice with these calculations, the easier they'll be. So A is my actual electrons around each atom present in the molecule. So carbon has 4, oxygen 6, and the other oxygen 6 for a total of 16 needed. Twice what they have, but not more than 8. So we're going to have 8, 8, and 8 for a total there of 24. Now just a little bit of basic mathematics. 24 minus 16 gives me 8. 8 bonding electrons takes 2 electrons to make a bond, so that would be 4 bonds total. And the leftover electrons, and this is total, a little bit different than that other process that we use for a halogen. We had 16, 8 of them are in bonds, so that tells me there's going to be 8 leftovers or 4 pairs. Again, divide that 8 by 2 to get 4 pairs total on the whole molecule and 4 bonds. So, central atom, draw the carbon, start with the single bonds. All right, now this tells me there's 2 more bonds present, so I've actually got multiple bonds here. And with that, we have a double bond there and a double bond there. There's the 4 bonds. Bonds first. So we've got our central atom bonded to our external atoms here. And now there are 4 remaining pairs of electrons. So I'm going to go back here. Each one needed 8. So the central carbon has 2, 4, 6, 8 when it has 4 bonds. So the oxygens, do they have 8? This oxygen here on the right has 2, 4, 5, 6, 7, 8. The oxygen on the left, 2, 4, 5, 6, 7, 8. And there's the 4 pairs of electrons. 4 bonds, 4 pairs of electrons. There's the structure for carbon dioxide. Next one that I'm going to do is sulfur dioxide. Sounds similar. Let's see what it looks like. Does it have a halogen? The answer is no, it does not. So we're going to use the non-halogen method, ANBBLP. 6 on sulfur, 6 oxygen, and 6 on the oxygen. Again, basing that on the group location on the periodic table, number of valence electrons. Total there is 18 needed. Double what they have, not more than 8. 8 plus 8 plus 8. Total 24. 24 needed, 18 present, so we subtract. 24 minus 18 means we need 6 bonding electrons. Takes 2 electrons to make a bond. 6 divided by 2 is 3 bonds. Leftovers, there were 18. 6 of them are in bonds. So 18 minus 6 is 12 leftovers, which would be 6 pairs of electrons. 3 bonds, 6 pairs of electrons in sulfur dioxide. Central atom sulfur, single bond oxygen, single bond oxygen. There's another bond present. In future lectures, we'll get into talking about a delocalized pi bond. For right now, there's a third bond. They're both oxygen, so we're just going to pick one side to draw this. Again, in future discussions and lectures, we'll talk about that delocalized pi bond. So there's our 3 bonds, 6 pairs of electrons left over. Let's go back up here. 8 around the sulfur. Sulfur has 2, 4, 6. So there is a lone pair present. The oxygen on the right has 2 electrons because it's single bonded the way we have it drawn in this structure. So it needs 8. So 1, 2, 3, 4, 5, 6, or 3 more pairs of electrons. And the double bonded oxygen, also needing 8, has 2, 4, 5, 6, 7, 8. Let's count the lone pairs. 1, 2, 3, 4, 5, 6. 6 pairs, 3 bonds. There's sulfur dioxide. And again, we'll talk about lone pair distortion and delocalized pi bonding and major resonance contributors and bond orders and all of that in the near future.